Now let's look at how we would use integration with polar to find the area of this little region right here. Okay. The region bounded by the outside circle, x squared plus y squared equals 16, the inside circle, x squared plus y squared equals 4, and then these two lines, y equals m1x and y equals m2x. Okay, so we want to figure out how we're going to find that area using polar integration. Now, first of all, remember that this right here in polar would be r equals 4, and this down here in polar would be r equals 2. So we've got these polar functions. Now remember, with polar, we integrate 1/2 from one angle, alpha, to the other, beta, r squared d theta. That's how we integrate with polar. So it looks like what I need to do is figure out what r needs to be. Now, if you look at this region, or this little region, the outside the outside curve is going to be the r equals 4. See, look at these little radii here. So if I do this, if I integrate 1/2 and I go 4 squared, from these things right here, from here to here, whatever this angle is, alpha to beta. If I do that, what I'm going to do is I'm going to get all of this area in here. I'm going to get an area of this whole sector, the circular sector right here. But I don't need the area of that whole circular sector. What I don't need is this part right here. So I need to subtract that off, which is what I'll do. I'll subtract off the 2 squared. And then d theta. Yeah, that's it. Well, there you have it. So we're going to get the outside minus the inside, and that's going to leave us just with that region. But the question is, from what angle to what angle? Okay, so let's just look and see if we can figure this out. Now, we're told that this is r equals m1x. Okay, so here you have x, this distance here, and here you have y, and here you have some angle down here, alpha. So here's what we have now. If you look at this, we've got y over x equals m1. Now remember, let's think about this. Tangent of alpha is equal to y over x. So it looks like that alpha is going to be arctan of y over x. Or in other words, I could just say arctan of m1. So I'm going to integrate from arctan m1. And by the same reasoning, you notice up here, we could do the same thing. We could say, well, this is x, this distance here is x, and the vertical distance is y. So this would be arctan of m2. So there's what we want to integrate. We want to integrate from arctan m1 to arctan m2. So what we end up having, of course, is we have 1/2 16 minus 4, that's 12. And we're going from arctan m1, whatever that may be, to arctan m2. Yeah, so that makes for a real simple problem. And I'm just being general here, so we don't know what m1 is, so we really can't go much further with it. I mean, I'll just leave it like this integral, but this is the general process and how we would deal with a problem like this. Now let's look at another problem. Here we have x squared plus y squared equals 4 and x equals 1. And what we want to do is we want to find the area of this little region right here, this little region right here. And it's bounded by x equals 1 and x squared plus y squared equals 4. So let's first of all, we're going to use polar here. So let's first of all convert things to polar. This is going to be y equals 2. Now this one, x equals 1, well, that's r cosine theta equals 1. See, I'll just convert that. That means that r is equal to 1 over cosine, or another way to look upon it is r equals secant theta. There we go. So now everything's in polar. So what we're going to do, we need to think about these little radii. Here's our integration where we've got these radii coming from here, and notice they're coming from the origin over here, the pole, and hitting this r equals secant right here. R equals secant until we get over here. Then these little radii switch over, and now they're hitting the circle r equals 2. So it looks like we're going to have maybe a couple of integrals here. Okay, so let's think about the first one. Let's think about when we're going this way. We've got these radii. Okay, so we're going to integrate 1/2 secant squared theta d theta. Okay, until we get to here. Okay, until we get to right there. So we're going to keep integrating, and then we get to this alpha right here. And then we're going to transition to this other r, and that's going to be 1/2 2 squared d theta. So we're going to add up those two things. This is going to require two integrals. What I need to do is figure out, well, what is this alpha? Now notice, obviously we're starting this integral at 0 and we're going to alpha. This integral is starting at alpha and it's going to pi over 2. That's pretty obvious. So I guess I need to figure out what alpha is. Now, let's see if we can figure that out. So here's one way I could do it. We know that at that point right there, we know what the x is. The x is 1. So let's do this. We've got x squared plus y squared equals 4. Now I'm just going to put a 1 in for the x. 1 squared plus y squared equals 4. That means that y squared equals 3, or y equals the square root of 3. So we've got a point here. We've got the point 1 comma square root of 3. Well, that's helpful, right? So in this triangle, we've got 1, and then this height here is the square root of 3. Well, it's pretty easy for us then to figure out what alpha is. Just some basic trig, right? Opposite over adjacent, inverse tan. So look, alpha is equal to arctan of the square root of 3 over 1, which that is going to be pi over 3. So now we know what the alpha is. So here's what we have. We have 1/2 0 to pi over 3 secant squared theta d theta. And then over here we've got 1/2 pi over 3 to pi over 2 of 4 d theta. And then it's just a matter of getting the antiderivative. And we know for this first one, the antiderivative of secant squared is tangent. And we're going from 0 to pi over 3. And then for that second one, we've got 2 theta. from pi over 3 to pi over 2. So yeah, just 4 divided by 2 is 2, and then I integrate it and get the antiderivative to be 2 theta. So I guess we might as well go ahead and finish this off. We've got 1/2 of tangent of pi over 3 minus 1/2 tangent of 0. Well, tangent of 0 is 0, plus 2 times pi over 2 minus 2 times pi over 3. And there you have it. Now, let's see here. 1/2 tangent of pi over 3 is going to be the square root of 3. And then we've got pi minus 2 pi over 3. So let's just work it out a little more. We've got square root of 3 over 2 minus, well, actually not, it's not going to be minus. It's going to be plus, let's see here, 3 pi over 3 minus 2 pi over 3. And we get square root of 3 over 2 plus pi over 3. Yeah, as long as I didn't make any mistake along the way, it looks like that's the area of that little region.